So now let's go ahead and talk about how this rate data might work and why it's actually maybe a more useful way of looking at Poisson regression. So rate data consists of rate that a number of events occur for some time period or other baseline measure. So some examples that you might be looking at is maybe your number of melanoma cases, so our skin cancer cases, over per given city size. Let me write this a slightly different way, even though it might look a little weird here at first. So let Y be the number of melanoma cases based upon city size. Or I might model Y being your number of customers per hour that you're opened, instead of just looking at your total number of customers in the day. Or I might model the number of weeds that someone has in their yard, but based upon how many square feet, so how many weeds per square foot. So we're really working with still this being our Y, but we're accounting for another measure, and that's what the rate data means, is we're taking into account based upon some other measure that we might be working with. And so because we might want to incorporate into the analysis, one way to do this is to model the Y over T instead of just Y by itself. So this is basically our Y now per T that we're modeling. So Y is still the number of events and T is the time period or baseline measure. And so how I would model this using the Poisson regression, what I would say then my log of mu in that time frame would be the alpha plus beta times x. Or we could rewrite that as just the log of mu, using our rules of log here, minus the log of t is equal to alpha plus beta x. So then when I would actually solve this for mu, we'd have a mu would be equal to t times e to the alpha plus beta x. Over here, this log of t is sometimes referred to as an offset. So let's understand this through an example. So we're going to get professor evaluations every semester. And so maybe one of the goals we would like to do is to predict the number of negative comments that a professor will get based upon how the students rated the professor on a scale from 1 to 5, where 5 is best. So I have my evaluation mean of the professor here on our x-axis and my number of negative comments on the y-axis. And so here's just a plot of what my data looks like. And I could easily fit a model to this, assuming it is Poisson. However, there's probably another variable out there it's very important in understanding how I might have the number of comments that I have, and that is just simply how many students does the professor have? I mean, if I'm only teaching 20 students, if I'm teaching 200 students, that's probably going to make a pretty big difference here to me on just how many negative comments I would expect to have in the first place. So what we've done here is I've now modeled the number of negative comments, and so I modeled the number of negative comments per 100 students. So I'm letting 1t that we're talking about here be 100 students. And so now I'm going to be modeling mu equal to t e to the alpha plus beta x. So in a sense, I'm kind of trying to make everyone on the same playing field by like, well, if you have a different number of students, you're probably going to expect a different number of negative comments. So let's now model your number of negative comments per 100 students. I don't really know why my titles got off in this PDF, so I do apologize. Hopefully yours look normal. So now I've got that plot that's different than what I had before. So you might not see that there's not drastic difference, but for example, these points here that are now between 15 and 20 were down here. So let's first talk about how I actually did that with my data set. So this is the data set that we're going to be using. So I just have the number of negative comments and the mean rating of that class. So this was my original Y and X that I was working with. A new variable that I'm now looking at is the number of students that were in that course. So now I created a new value. Instead of just looking at the number of negative comments, I have the negative per 100 students. So how do we actually calculate that value? So this is going to be my number of negative comments times my 100 students divided by the 45. And then I just sort of dragged this for all. Oh, it doesn't automatically do it here because I put in the numbers. Let me just click instead. So this is going to be equal to this value times 100 divided by this value. And that way I could just drag that function and get it for all of my values. So I can see here, so if I had 45 students and 8 negative comments, I would expect about almost 18 negative comments if I would have had 100 students. Here we already had more than 100 students and we got 33 negative comments. So if it was just 100 students, I would have gotten 30 negative comments. So we're kind of putting all of these values now on the same idea of the number of students. So it might make it a little bit easier to compare here. So that's how I created it here in Excel myself. And then I did that before I went to R. So now looking at our two plots. So again, here maybe we didn't see a huge drastic difference between my two plots. So here's my original one, which was just the number of negative comments. And then this is our one where we've taken into account how many students the professor had. There's a little bit more of a trend, especially early on. Early on here, there was a lot more scattering going on. But now with our new plot, it seems a little bit more like there's this pattern going on a little bit better. So what I might make for my comments here about these graphs is we appear to have a little bit less variation when we used T. And we might also be able to kind of notice a little bit more of this negative trend that hopefully makes sense that the higher the evaluation of the professor, the less negative comments that we would expect to see. So this idea of trying to use T to help us model can be useful to help to account for possibly another variable that seems to be quite important when modeling your different values. So for example, if I was looking at like the modeling the number of typos that a student has in a paper, I might want to take into account first how many pages long is their paper. And so I might look at the number of errors per page instead of just looking at the total number of errors made. All right, so let's go ahead and fit both of these plots here in R. So I've already loaded in my data set. So this first one here is just looking at the number of negative comments by evaluation rating. And then the second one, all I've done different is now I'm modeling that different response variable here that takes into account t. And so because I liked this second plot better, and here's nice, you kind of go back and forth this way a little bit easier to see how that variation maybe went down a little bit more. I'm going to actually use this in my GLM. I'm going to use then the number of negative per 100 students instead of just the number of negative comments. So I'm going to fit my model again using that Poisson family with the log link function. Same other values here, and I'm going to spit out that summary. And actually, my first just fit the model because this does freak people out when they first see it. You're going to see that there was all these warnings, and it says you can use warnings parentheses to see them. Oops. So here was what these warnings were. So the warnings here took into account that they knew we were using the Poisson family, and the Poisson models count data. But you gave me a whole bunch of x values, technically are y's, but they're calling them their x here, that were not whole count numbers, right? So originally my data set had just the number of negative comments, but now that we're modeling this number of negative comments per 100, I actually have decimals as values, which they say that doesn't make sense if you're working with a Poisson distribution, so that's kind of just giving you that warning. It still fit everything, it's just warning you that they had some numbers in there that didn't seem to make sense because they weren't integers that they were working with. So we're okay with that here. Now just running my summary. Again, I'm mainly focusing on this alpha hat and beta hat that I'm going to be working with there as well. So we're going to use that output to write out our prediction equation here. Alright, so our mu hat is now going to be firsting having that t in here. And then we're going to have the e raised to our alpha hat, which was just 7.47. This time minus, since we had that negative relationship, 1.484 times our x. Now this might bring up the question of like, well, how does this t then actually play a role in finding these predicted values? So let's understand how we would actually do that. So if I wanted to find the predicted number of negative comments, if my mean evaluation rating was 3.65 and I had 100 students. Well, what this means for me is my t is going to be equal to 1. Because I'm looking at per 100 students. So if I have 100 students, my t is going to stay 1. So then my mu hat is just going to be 1 times that e to our 7.47 minus 1.484 times our evaluation rating of 3.65, giving us 7.79. If I want to do my mean evaluation rating of 4.35 with 100 students, my t would still be 1, because we're still working with 100 students. So the only thing that actually would change here in our equation from above is that evaluation rating that we're going to plug in. Now I would expect my answer to be less than 7.79 because I have a higher evaluation rating. And so we would get 2.76 here. Now, how does a different number of students actually factor in? So if I'm looking back up here at my mean of 3.65, but this time I only have 50 students, my t is going to be 0.5 because I only have half of that students. So again, so then I'm kind of thinking about, so what t is going to be looking like? That's going to be our number of students divided by 100. That's how I'm going to find out what to plug in for t. So this time my mu hat is going to be a half times this e to the 7.47. Which then should also just turn out to be a half of our 7.79 that I found above. So I would expect half as many negative comments with 50 students as I did with 100 students for the same mean rating. So that's why those turn out to be, because it's the exact same mean rating. So if I'm looking now at my number of negative comments expected with 50 students and a mean rating of 4.35, again my t is going to be a half. But what I know I'm going to get a half of what I had up here because it's the same mean rating and my t is half of what it was before. So my mu hat is just going to be a half of the e to the 7.747 minus 1.484 times our mean rating of 4.35. So we're going to get out half of our 2.76, which is our 1.38. So this way you are allowed to use, and essentially kind of two different variables to help you look at the number of negative comments, but where one is really just something that it's not really something that you get a control that you want to predict based upon, but you still want to know how many students that the professor had to understand why they would have the number of negative comments that they do. Right, so again, the main goal here was to kind of get a very quick introductory look at Poisson regression to first understand that there are other generalized linear models that are not logistic regression, that they don't have to be linear regression. There are ways of modeling other types of data to be working with. You do not have homework over Poisson regression, however, it is still fair game for the final exam, so please let me know if you have questions. The main reason you're not doing homework on it is I don't know if I would have enough time to get you feedback and turned around before you actually take your final exam. So please let me know if you have questions looking at the Poisson regression note.